let's get started. See that? Take that, Corona. We out here. We grinding. We still here. Okay. All right. I don't even want to erase that, but you know, I'm gonna need the board space. So
we can just draw a square on that.
just and just write math notes all around it. Yeah. Okay. Okay. All right. Let's go. Last time. Yes, I'm not even sure what I'm actually going to do here. I figured what I would. This is the initial idea. Continue to record lectures, just lecture to an empty classroom, and just like have you guys comment with questions or something like that, and then I pick up with the next video answering the questions at the beginning. So it's kind of like questions get deferred or delayed. I don't know. So something like that.
So our comments will be the questions?
Yeah, you send me questions, but I'll have to think more about how to streamline that. I think the department wants us to do something a little more interactive, but...
Oh, no.
Yeah, I don't know. I feel like that's going to be really awkward.
Blackboard?
Anyway, so we have I guess I have until the 19th to come up with an idea and let you guys know. But in the meantime, let's continue. Last time, we learned about series. Now, series, these guys were just the sum of the terms of a sequence. The ones we care about were infinite series, and they would look like this, for example. A1 plus A2 plus A3 plus ... So we're just adding up an infinite number of things where each thing is given by some formula when you plug in n equals a certain number. So that's what we're looking at. We saw what it means for an to converge. So if we see that the series an converges, means Sn approaches S, where S is a real number, Sn is the sequence of partial sums, of an, and we write and is equal to S. Right? So convergence means we add up the first n terms and then we keep adding one more term and one more term, and we look at what that approaches in the limit. If it approaches a real number, we say the series converges, and we say it converges to that number. So we can say it converges to S. And we can write this equals S, and what it means is the sequence of partial sums converges to S. We also saw what it means to say that a series converges absolutely. That's an important definition. So that phrase, very important phrase, this means that the series with absolute values around each term converges. Meaning there is a number S that works for the series with absolute values around it. And I'm going to leave this up. Going to leave that up. Okay. And we say this guy converges conditionally. So that's another phrase that we have, and that's if an converges, but the series with absolute values around it does not. And the only other scenario for us is an diverges. We say the series diverges. Now, absolute convergence is important because there's an important rule that we are going to need that only works for absolutely convergent series, namely commutativity of addition. The fact that you can add things in any order and always get the same answer, in the case of infinite sums, is only true in the absolutely convergent case. It is actually not true in the conditionally convergent case. So that's something that's important. If we care about commutativity and we want to be able to change order and not worry about getting a different answer, we want to be able to look at an absolutely convergent series. So that's the next. Those were important ideas. We also saw one specific kind of series, and we found out what it converges to. This was a telescoping series. But that was just the beginning of a journey that's going to bring us to important places. It is important. And you'll see some reasons why to know if a series converges. And to what it converges. Now, the to what question is actually a very difficult question to answer in general. We know a few cases on how to do this. At least, in this class, we learned specifically 2 ways in which we can know exactly that answer. But the if question is a little bit more accessible, and that's what we're going to focus on for the most part. It's a very difficult question to answer. The if is easier to answer. And this is the focus of, in your textbook, sections 10.3 to 10.6. We're going to go through several different what we call series convergence tests to test whether or not a series converges. Not all of them are going to tell you to what it converges to, but you are going to know that there exists a number S such that it converges to S. And then after that, I will talk about pretty much estimating series. How can we know that we're getting close to S, or what S might be, or within some tolerance level? Because figuring out exactly what S is difficult in general. And most of the time it's above our pay grade to talk to. So, yeah. So, I'm going to tell you about this leads to what we call the series convergence test. These tell us what a series might converge to. It also tells us whether or not a series converges. Now, test number 0, I'd call it because it's kind of an odd one out. This was the telescoping series, and I told you how we can find those things. So that's a particular series where if you write out a sequence of partial sums, a lot of terms cancel out, and then you can take the limit of the remaining terms and come up with an answer. So it's a very nice kind of series. It is one of the few types of series, one of 2 to be specific, one of the 2 kinds of series that we'll be able to tell exactly what it converges to in general. But the others are not as straightforward as that. So let's talk about some of the others. So that's what we're going to do. So for the next 2 or 3 classes, whatever those might look like, we're going to be going through all these different tests that if I give you a random series, would you know if it converges or not? It's very important that we answer that question. So let's talk about the first test. So there's a test called test for divergence. You might see it by other names, aka the nth term test, or the kth term test. You might also see it called the limit divergence test. Various kinds of tests, various kinds of names here. But I like this name the most because it pretty much tells you what it's about. It's a test for divergence. It's going to be a test that can tell us when a series is going to diverge as opposed to converge. And here's the test. Suppose AN is a series. And of course, like I said, for the rest of the class, we're talking about infinite series here. Even if I don't mention it, we're always considering infinite series. Finite series aren't very interesting. Then, if the limit of AN is not equal to 0, then the series diverges. That is the test. And what limit? It's always limit as you approach infinity. Remember we mentioned that, limit as n approaches infinity. And that's pretty much it. Let me give you some examples. So, first test we're going to do, it's actually one of the easiest tests to apply. It only requires knowledge of limits, which as of Calculus 1, you guys should all be experts at. So, basically it says, given any series AN, any infinite series, if the limit of AN is not 0, the series will diverge. You can just conclude that it's going to diverge. There will be no real number S, such that its sequence of partial sums will converge to S. Let us do the first example. N to the n over n factorial. So you see that. Note, the limit of n to the n over n factorial is going to be infinity. Right? So last time we looked at that list, remember, logs are smaller than polynomials, are smaller than exponentials, are smaller than factorials, which are smaller than variable exponentials. Right? So guys on the right, as n goes off to infinity, they're essentially infinitely bigger than guys on the left. So this guy, as n is going off to infinity, is huge compared to this guy, and he's in the numerator of this fraction. That fraction goes to infinity. And so, basically what you could say here, the series diverges. That would be your answer. That's basically it. That's all you have to do. You see a series, you take the limit, it's not 0, it will diverge. B, if you look at this series, it goes from 1 to infinity of 5 minus 7n plus 3n cubed over n cubed plus 2n squared plus 1. Note. What is this limit?
3.
It's 3. In particular, not 0. This means the series diverges. Now, this is going to be a theme. I mean, so far this doesn't look any really scary. And you're going to notice any one test that I'm talking to you about, it's not going to be terribly difficult to actually do the test. The difficulty comes in when I give you several different kinds of series and you try to figure out which test you actually want to use on it. That's where the difficulty comes in. So we're going to go through a bunch of them, like 10 of them, and individually they're not going to be hard to put together, but it's kind of like the techniques of integration. Although integration is probably a little harder either way. But it's not that knowing one particular technique is the issue, it's that when I give you several integrals of a variety, how do you know which technique to try? With series, it's going to be the same thing. So this is the test for divergence. It is actually one of the easiest tests to actually do, and it pretty much amounts to checking the limit of the sequence expression, and if it doesn't go to 0, it diverges. The third example. What is the limit of the absolute value of sin squared n? No. Do you know what sine squared looks like? It's like a sine graph, but it doesn't have any of the negative parts, right? So it looks like this. Huh? So what?
It's just numbers.
So what do you say is the limit?
Right?
What?
Huh?
Doesn't exist.
Oh, yeah,
Does not exist.
no.
It's not 1. Limit is a y value that you approach as you get closer. For you to say that the limit is 1 means that eventually it starts to settle at 1 and never get close to anything else, which does not happen, right? This thing literally just keeps bouncing up and down. There will always be points that are close to 1, but there will also be points that are very far away from 1, literally forever. Limit does not exist here, but that's still not 0. So the series diverges. Here, limit, well, 1 over n, what is that? That's 0. What does this mean?
Could either
Might converge and
It might converge, it might not. Turns out, no conclusion here. Right? So here's where I give you a warning about the test for divergence, is that it is literally a test for divergence. You cannot use that test to talk about convergence. That's a very important thing. So, warning. If the limit of an equals 0, it does not mean converges. In fact, the counterexample to this is very typically that guy. Pretty much every textbook that talks about the fact that this is not true, that's going to be the first example that they point you towards. That's actually a very famous series. It even has a special name. Does anyone know the name? Huh? It is a pSeries, but it's a very special one. It has a special name besides it. So, common counterexample here. Is the series 1 over n. N goes from 1 to infinity. It is called the harmonic series. It is a pSeries where p equals 1. We'll talk about pSeries later. We probably won't get to it in this class, but maybe next class, whatever that looks like. So, this particular series is called a harmonic series. Now, if you were to start adding out the terms, it would look like 1 plus a half, plus a third, plus a fourth, plus. And here's what you have to remember about the harmonic series. It is known to diverge. This actually diverges. So this is an example of a series whose limit of the sequence goes to 0, but the series does not converge. We know that this diverges, and I'll show you one way to prove that, but for now, just know that that's a very important example. Harmonic series, you use it a lot in signal processing, auditory processing, that sort of thing. That's where the phrase harmonic comes from. It's actually very important in such applications. But that's a particular series that shows you the test for divergence, the opposite conclusion is not the case. So we do know that if something converges, the limit must be 0, but we don't know if the limit is 0, then it must converge. That's not actually true. So it is true if an converges, then the limit must be 0. But limit of an equals 0 does not mean the series converges. You have to test something else. You don't know. Another example that people like to talk about pretty much right after they talk about the harmonic series is that they make a slight tweak to it. And instead they square the bottom. This is an example of a series. The limit goes to 0, right? So 1 over n squared approaches 0, and this series is known to converge. So we know that this one converges, and we're going to prove that it converges. Also, I'm not going to tell you what it converges to, at least we're not going to prove what it converges to. So this guy is like 1 plus 1 over 2 squared, plus 1 over 3 squared, plus 1 over 4 squared, plus that. The idea being, the nuanced idea is that yes, the terms are going to 0, but they don't go to 0 fast enough, so you're always adding something very big. Once you square the denominators though, all the terms go to 0, and they go to 0 very fast to the point where you quickly get to a point where it's like you're adding nothing after a while. That's actually going to converge to a number. In fact, it's known to converge to, who knows what number this is. It's really weird, totally unexpected. Pi squared over 6 of all things. Yeah, you have an infinite amount of rational expressions. You add up a bunch of fractions and you get something that cannot be expressed as a fraction. Kind of weird, but it's actually true. We're not going to prove that. Where would you prove that? Maybe in complex analysis. Maybe. Complex analysis or real analysis or something like that, you prove it. But You should know that it converges. You don't have to know what it converges to, but just for curiosity's sake, it's pi squared over 6. 1 over n diverges, the series of 1 over n. It's called a harmonic series. A very important example. You would want to know the name. So be careful with the test for divergence. You should know that it can only tell you about divergence, because it's possible for the limit to approach 0 and it diverges, or the limit approaches 0 and it converges. Knowing alone that the limit converges to 0 doesn't really tell you anything. It can go either way. However, knowing that the limit is not 0 definitely tells you it diverges. So that's the first test. That being said, and once I tell you about all the tests, I'm going to actually summarize when you might want to use one or the other. But just in passing, I'll mention that test for divergence is going to be one of the easiest tests to apply. It's going to be one of the things you want to try pretty much first. So I give you a random series. The first thing you're going to look for is, does the limit go to 0? That's the first thing you want to look for. Because if it does not go to 0, you know it diverges, then you don't have to do anything else. If it goes to 0, you can't make any conclusions, you have to do something else. But it's one of those things, kind of like integration by substitution. It's one of the first things you try all the time, because it's one of the easiest things to actually apply. So that was the first test. Test for divergence. That tells us when something diverges. It can't tell us when something converges. Next one I want to tell you about. So, test number 2. This is called the geometric series test. But what a geometric series is. It has a very specific form. There are two ways that it's usually expressed. One, it can be a series going from 0 to infinity, and then the terms would look like a times r to the n. Or you can start it from 1 to infinity, and in that case write as ar to the n minus 1. The idea is you want the first term to be a. You want r to the 0 to be the first guy. So depending on where you started, you would actually shift the powers to actually coincide with a being the first term. You will notice that if you were to multiply these guys out, it looks like a plus a times r plus a times r squared plus a times r cubed plus keep going. It's what you get if you start with a number and you keep multiplying that number by the same thing over and over. So you start with a, multiply by r, that's your second term. Multiply by r again, that's your third term. Multiply by r again, that's your fourth term, and so on. It keeps going. Right? So this is called a geometric series. Here, a and r are constants. Okay? So they do not involve n's. Right? So when it comes to the series, the variable is the n term. So a and r are just numbers. They're real numbers. Let's figure out the convergence of this. So this is a nice one because the proof of when it converges is not too difficult. In fact, it's the same proof that we used to. So we use a similar idea. As we did to show the sum of the first n integers is n times n plus 1 over 2. And as we did to show basically means I did it in Calc 1. So when we were talking about Riemann sums, we used that was one of the formulas that we needed, and there was a special trick that we used to figure out that that was true. We're going to use a similar trick here. So it's the same trick which legend has it. Baby Gauss used to add up the first 1,000 integers in only a few minutes. When his teacher gave him the busy work of adding the first 1,000 integers. The baby, it should have taken him all day. He did it in a couple minutes. What did he do? Well, let's look at the sequence of partial sums. So what would Sn look like here? A plus A squared. Let's just take the first few terms. And here's something that we can do. Because it's kind of very self-similar, we can multiply this equation by r. We get AR squared, AR cubed, all the way down to AR to the n plus 1. And then what we like to do is we subtract these two. So here, let's call this equation 1. Here, let's call this equation 2. And what I'm going to do is I'm going to take equation 1 and subtract equation 2. This leaves us with Sn times 1 minus r. And over here, what happens is, well, a minus nothing, the a is just there. But this subtracts that, this subtracts that, this subtracts that. And it goes all the way down to this guy subtracts the guy right before this. And we're left with that. In fact, now I can solve for the partial sums, and it gives us a nice formula. A1 plus r to the n plus 1 over 1 minus r. So now, we want to know what does this actually converge to. Now remember that a and r are constants, which means this part here is a constant, which means the behavior of this limit is going to greatly depend on this expression here, which has the n in it. Right, so that's an r. What can you tell me about that expression as n goes to infinity? What is that going to look like? Ideas?
Does it go to infinity?
But there is one case where it goes to infinity. Sure, because let's say r equals 2. Just throwing a number out there, right? So that guy's going to look like 2 to the n plus 1. Well, what does that look like? Well, if you're graphing n versus an, that would look like, well, exponential. Is that the only possibility? Of course, if your r was 0, it's actually never actually 0. I should have mentioned that. A and r are not 0 because otherwise it's kind of silly. But if r was 0, it would just be a horizontal line like that. So I would just go to 0. Any other r values that you can think of? What else can you try? So if your r is 2, it actually approaches infinity. Can you think of any r value that will cause it to not approach infinity? Yeah.
1 also.
Well, if r is 1, then what you would have essentially is 1 to the n plus 1. Now, as n approaches infinity, your Sn would approach, a part of the Sn, would approach 1 to infinity. What is 1 to the infinity?
Like indeterminate.
It's indeterminate, so we get gibberish if it's 1. Any other ideas?
Any fractions?
Like?
I don't know, like 5 by 4 maybe?
Give me a fraction.
5/4?
5 over 4. Okay, so what would happen to 5 over 4? If I have 5 over 4 to the nth power, as n goes to infinity, what is going to happen to that? It also approaches infinity. Right? Because you have something bigger than 1 that you keep multiplying by itself. It's just going to keep getting bigger and bigger. It's like you're multiplying by more than 100%. It's going to just increase.
Anything less than 1? Not a negative number, but
I mean, like r equals a half.
yes.
Take a half to the n, what does that approach? Approaches 0. Because you take a half of a half of a half of a half. It just keeps getting smaller and smaller. What about, so you don't want negatives, what about minus a half? What would happen if I take minus a half and keep multiplying by itself? It also approaches 0. Of course, it bounces up and down before it approaches 0. But we saw last time that if the absolute value of the sequence approaches 0, then the original sequence will approach 0. So it makes sense that that approaches 0. So negatives by itself aren't bad. In fact, here, if I put a minus 5 over 4, what would have happened here? Minus 5 over 4. Now this is an issue because that is actually growing to infinity. It's going to be plus or minus infinity. It's going to bounce up and down. So here you'd say it does not exist. But this negative is not a problem because it actually approaches 0. 1 is an issue. You get an indeterminate form. Anything bigger than 1 is clearly not going to be an issue. So what can you say is a safe R value to get some sensible answer? Give me a range of R values that's going to give me something meaningful.
Between -1 and 1.
It's strictly between -1 and 1. Because if that is the case, if my R value is strictly between -1 and 1, that part there, the R to the n plus 1, actually goes to 0. Now notice, if R, and one way you can actually say that is saying the magnitude of R is less than 1. So that's saying R is between -1 and 1. Then R to the n plus 1 will approach 0. And in this case, your Sn would approach. So what is the Sn here? If that R to the n plus 1 is going to 0, what does Sn approach?
0?
No.
No.
Huh?
It approaches S?
So Sn is this whole thing, right? That whole thing is Sn. Right? This whole thing right here is Sn. Now if you know this part is going to 0, what happens to, what does the whole thing approach? No. You see what's happening here? This part is approaching 0.
It approaches A over minus R.
It approaches A over 1 minus R. Otherwise, Sn is going to approach infinity, or it's not going to exist. So that tells us about the geometric series and where it actually works. This leads us to the geometric series test. given the series AR to the n, if n starts from 0 to infinity, or n starts from 1 to infinity, of AR to the n minus 1, where AR are not 0, are constants. The series converges. In fact, as you can see, whether we have the positive or negative actually didn't matter. So not only does it converge, but it actually converges absolutely. Because whether I was strictly between positive 1 and negative 1, even if I was negative, it would still approach 0. The result would actually be the same. It converges absolutely if and only if r is less than 1 in absolute values. And it converges to a over 1 minus r. That's always what it's going to converge to. And by the way, this is the second instance in which I mentioned that we're going to be able to tell that a series converges and also know what it converges to. So besides the telescoping series, this is the only other one where we can actually know what the answer is going to look like. The geometric series, the answer is always going to look like that as long as r is less than 1 in magnitude. This one is actually worth a few examples because it's not always going to look so clean. So let me have you guys work through some examples here. Determine if the following converge. If so, state to what they converge. And here are some examples. So series n equals 1 to infinity of 1 over 2 raised to the n. Series n equals 1 to infinity, or n equals 0 to infinity. 1 plus e to the n over 4 to the n plus 1. Series of 1 to the infinity of e over pi to the n plus 1. And d, the series described by 1 minus 3 over 2 plus 9 over 4 minus 27 over 8 plus dot dot dot. Now it turns out for all of these, you'd be able to apply the geometric series test, even though at first they might not look exactly like you would expect it to. volunteer to do one of these? Can get 4 volunteers, yeah? You want to try which one? You want to do B? You already called it. Okay. So B is taken. Who's going to try A? Anyone want to try A? Volunteers? Come on, be brave. Try A. Someone try C. Okay, so we have a volunteer. Who wants to try C? Come on, we got to show Corona. We're fighting back. Come on. Come on, someone. Yeah? Okay.
I'm probably not going to get it right.
It doesn't matter. The attempt is what's important. D? Someone else want to try D? So it's probably our last in-person class. Come on. Gotta go out with a bang. You're gonna try? Okay, good. All right. So what I'll do, I'll give you guys 4 minutes to come up with your answer. And then we're gonna go over them. Now the rest of you who didn't volunteer also try to do it. Whichever one looks the scariest to you, try that one. And then see if you got it right. After we do it. I'll give you guys 4 minutes.
Jhevon,
Yes?
A is the starting term, right?
A is going to be the first term, yeah. If you plug in n equals 0, it just starts at A. Then you plug in n equals 1, then 2. Similar thing here, if you plug in n equals 1, you get r to the 1 minus 1, so you get r to the 0, so it starts at A. So A is the first term, that's how you can even think of it. So A equals first term. R is what's called a common ratio. It's called common ratio because if you take a n plus 1 and divide by a n, you always get r as the answer. So it's just a ratio that's consistently throughout the series. Anyway, trying is important. If we move online and I post videos and the virtual Jhevon tells you, hey, pause the video and try this, you need to pause the video and try it. It's important. It's super important. You won't believe how important it is. about 2 minutes left. Okay, let's begin. Who had this one? Yeah, well, what did you get?
I put it in convergence to 0, but it's kind of wrong.
Converges to 0?
Yeah.
How did you get that?
At first I thought we were going to keep getting smaller, but it starts at 1/2, so it's going to start with 0.5, but then it's going to keep getting smaller, but it's still really.
Yeah, the sequence is approaching 0, but the series is not, right? Because I mean, even if it's getting smaller, so this, what is it going to look like? It's going to look like 1/2 plus a 4th plus an 8th plus a 16th plus. At this point, you should actually recognize this example, right? This was the dichotomy paradox example, right? You walk a mile by going to half a mile and then a quarter of a mile, blah, blah, blah. We actually know this adds up to 1. We did this last class. Now, to deal with the other issue, so you notice that these guys were getting smaller. So each of these terms individually, an is approaching 0. But the series doesn't care that they're approaching 0. It already added a half. And then it already added a quarter. So it's at least that big. Now it's at least this big. So even though you're adding smaller and smaller terms, you're still accumulating some stuff. So it is building up to something, right? So the terms are going to 0, but the summation is not, right? The summation is accumulating stuff as it goes on, right? Now, we know that it accumulates up to 1. Now, that being said, how did we actually showed how we got 1 last time, but it was a very tedious process. It turns out for this same thing, we could actually use geometric series to get to the answer quicker. And we were in the section for geometric series test, so I probably wanted you to look at this as a geometric series. Now, if you're looking at this as a geometric series, what would the A be and what would the R be? Yeah.
Your A would be 1 and your R would be 1/2.
What is A by definition?
The first term.
The first term. What is the first term? It's 1/2. Your A is definitely the 1/2, right? It's the first term of your geometric series. So it starts at a half, and there's something that you keep multiplying by to get everyone else, right? What do you keep multiplying by? You keep multiplying by a half. So and then you know that R equals a half. You keep multiplying by a half. So you start with a half. A half times a half is a quarter. A quarter times a half is an eighth. An eighth times a half is a 16th, right? So you start out with a half, and then you keep multiplying by a half. Now, is there some way that if you didn't have that insight, like if you didn't even think of writing this out, could you have noticed that from this? told you a geometric series has two forms. It looks like AR to the n, if your n starts from 0. Or it's going to look like AR to the n minus 1, if your n starts from 1. Which form do you think we want to aim for here? This starts from 1, which means let's get this to look like that guy. Now, how would I get this to look like that guy? You factor out a half, right? Now, what are you going to have left over? Well, a half to the n minus 1, right? Or another way to think of that is a half times a half to the n minus 1. So you have a definition. If you want to make a conclusion, make it look like the definition, right? That's an idea that we've seen before. We do that with integration all the time. That's what substitution is about, right? You substitute this expression to get it to look like a rule that you have. That is a rule. I know that this is equal to a over 1 minus r. This is equal to a over 1 minus r if my r is less than 1 in absolute value. So that's a rule that I have in my head for the geometric series. Looking at something like this, I want to make it look like the rule before applying that. This here now, that's my a, that's my r. Right? I just see the exponential and I kind of write it in a nice form. Notice you have a constant times a constant to the n minus 1. The series starts from 1. That's geometric. What does it converge to? Well, it converges to a over 1 minus r, which is a half over 1 minus a half, which is 1. And we know that it converges to 1 since your r is equal to a half, and a half in absolute values is less than 1. So that's a much quicker way to tell that that would actually add up to 1. Notice that it's a geometric series. So the dichotomy paradox is solved yet another way. This is how we can walk a mile. Just think of a mile as a geometric series. There are other nice little examples that we can do here. The fact that 0.99999 forever is actually exactly the same as the number 1. We use geometric series to prove that too, and a lot of nice little problems can arise here. But the idea first is you have a geometric series, write it in the form that's going to make it look like one of those guys on top, and then provided your r is less than 1 in absolute values, the answer is going to look like this. But you need to figure out who's the a, who's the r. In order to do that, write it out like this. See, that's that. What's your last name? Yeah.
K-A-R.
K-A-R. And I believe it was, did you help on the, what's your last name?
Quinteros, Q.
Huh?
Q, Quinteros.
Q?
Yeah.
Q-U.
Q-U-I.
Q-U-I.
Yeah.
I'll give you guys an extra quiz point for your participation. Got it wrong, but the attempt was the important part. In the future, you have to get it right. But for today, you know, it's a special day. We're being very lenient. What about B? What did you try here?
So I can only get it if, is it okay that I do summation by parts and split up two summations? Or,
Is that legal?
yeah, so,
Yeah, we had that as a property last time.
So-
So that is allowed. You can do that anytime. Whether or not it's useful is another story, but you can always actually do
I
it.
had to break that up into 1 times 1 over 16 to the n plus
1,
over 1 over 16 to the n.
how did you get 16 to the end?
Because I took out one of the n's, or n plus 1, I took one out, make it. Oh, crap, no, never mind.
So, what?
No,
So I guess you just want to add across the numerators, was your idea, right?
Yeah.
So what is this guy? Starts n equals 0.
So that one is 1 quarter, and a is 1/4. R.
So it's 1/4 times
1/4 to the n.
1 over 4 to the n plus,
And then that is 1/4 e over 4 to the n. There you do the same thing, a over, because both of those r's are less than 1.
right, so here, the 1 over 4 to the n you can write as
Yeah.
that. Yeah, so this here looks like an a and an r to the n, starting from 0, so that's a nice form. Here, this is like an a and this is like an r to the n, starting from 0, so that's a nice form. We want it to the nth power. So because the power is n plus 1, the trick was to factor it off, right? So you know that 4 to the n plus 1 is just 4 to the n times 4. So you factor off a 4, and you get that. So this is actually 2 geometric series in disguise. You break them into 2 parts, and so tell me about the first one.
So it would be a over 1 minus r, so it's quarter over 3 quarters.
Over,
3 quarters, or
well, 1 minus a quarter, let's write it out. And then this one,
and this one is 1/4 over 1 minus e over 4.
so can multiply by 4 over 4. It's going to be 1 over, well, 4 minus 1. And that is a third. This one, if I multiply by 4 over 4, I would get 1 over 4 minus e. And, oh, that's just 1 over 4 minus e. So that is convergent because our r is less than 1 in absolute value in both cases. Here we have a quarter, which is less than 1 in absolute value. That's pretty obvious. E over 4 is actually less than 1. You have to remember that e is roughly 2.71828. E is a little bit less than 3. So e over 4 is going to be a little bit less than 1. And so that is going to converge as well. And what do they converge to? A over 1 minus r. So this is a series that we can actually know what it adds up to. And it adds up to that. Right? So, and this is a guy that looks like, well, 2 over 4 plus 1 plus e over 4 squared plus 1 plus e squared over 4 cubed plus da da da. You keep adding up a bunch of things like that forever, and it's going to add up to this number. So that's interesting. That's a geometric series. What was your last name? Think. Heaven. Okay, who was next? Who did C? Joel? What's your last name?
James.
Okay, where'd you get with C?
So I tried to make it into the form of a times 1 to the n. So I took out 1 over pi.
So you factor out 1 over pi.
Yeah, and then we multiply that by the e. From there, could you make that e over pi to the n like you did for the first one? Or no? No, you can't. But then after I was stuck with that, I tried finding a and r. So a was a over pi squared, right? Because I found the first term in the sequence. And then r was equal to 1 over pi, which is,
Yo, how would you get that here?
oh yeah.
And do you want things to the nth power?
I wasn't so sure if it was n or n.
Well, we had n equals 1 here where we're starting.
Right.
So what does the form need to look
It
like?
should be n plus 1 in order for the first term to be
N minus 1.
n.
You want to write things so that the power of r is n minus 1. How would I get like an n minus 1 power? Yeah?
So from the beginning, I took out e, and then so I was left with 1 over pi n plus 1, and then I separated that into 1 over pi squared, and 1 over pi both things n minus 1.
Yeah, the thing is, factor out another pi to get pi squared. That now becomes n minus 1. And at the same time, factor out the e. So here you have e over pi squared, which technically is going to be the first term. I could even write it inside, just to make it look more like the form. E over pi squared times 1 over pi to the n minus 1. Knowing that I'm starting from 1 means I want the power to be n minus 1. Factor out however many things I need to get the power to look like n minus 1. I'm trying to get it to look like a certain form. The e doesn't have an n on it, so just factor it off. It's a constant. So we have that. Now that looks like a number times a number to the n minus 1, which means that this guy here is your a, that guy there is your r. Is r less than 1 in absolute values? Yeah, 1 over pi is definitely less than 1 in absolute values. So this actually converges to a over 1 minus r. So this is C continued. So this is equal to, I can multiply top and bottom by pi squared. So this would look like E over pi squared. So that guy converges to that number. D. Who had this one? Yeah, what did you do?
I basically said it diverges because when I looked at the common ratio, it was like 3 by 2.
Okay.
And like the absolute value, negative 3 by 2 is like basically 3 by 2 is like greater than 1. So that's why I don't know if I'm right.
Well, you have a couple ways. Yeah, so just notice that you kept multiplying by 3 over 2, negative 3 over 2, right? That's why the sign is alternating. So you took 1, you multiply by negative 3 over 2, you get this, multiply again by negative 3 over 2, you get that, and so on and so forth. So pretty much notice that this is like negative 3 over 2 to the 0 power, plus this is negative 3 over 2 to the 1 power, negative 3 over 2 to the 2 power, and so on. So one thing you can notice. you could also notice, yes, this is, the first term is A, and R is the common ratio, which you notice is multiplying by that. So you can actually look at it like this. So here, you know that this is diverges. Since absolute value of R is equal to the absolute value of 3 over 2 minus 3 over 2, which is bigger than 1. So that one diverges. So yeah, those four were all used, we figured these all out by using the geometric series. So the worst thing you have to worry about here is remembering your algebra, know how to actually finesse things to look a certain way by factoring things off and so on and so forth. What's your last name?
Mike, Anthony.
Huh?
Anthony.
So that's the geometric series test. Knowing the formula and knowing what it converges to, knowing when it converges, these are all important things. After that, it's going to be just algebra, knowing how to deal with exponents. Also, like I said, this is one of only 2 situations in which you're going to know what the series converges to, which means you can kind of even use the way a question is phrased as a hint that you might want to look at this. So there are times when I would say, tell me what the series converges to, as opposed to just tell me whether or not it converges. So if I ask you a question like, tell me what this converges to, it means it can only be one of 2 things. It's either telescoping or it's geometric. Now, telescoping is going to be something where you can try like a partial fractions on it or something like that, so chances are it's going to look rational. And once you have like an exponential, you know it's going to be geometric. So that kind of narrows the playing field down for you, right? So geometric series, the second situation in which you can actually know exactly what something converges to. We don't have many of those in Calc 2, so that should stand out to you. So it's a very different thing if I ask you if something converges as opposed to me asking you what does it converge to. The moment I say that for a series, it's probably one of 2 situations. Let's move on to another one. So we did telescoping, test for divergence, and geometric. So 3. The telescoping was 0, test for divergence was 1, geometric is 2, 3 is something called the integral test. Right? Because I know you guys miss integration, so let's actually bring it back. Here is where we pretty much use an improper integral to tell us about a series. So that's going to be interesting. So, given a series AN, and again, it's an infinite series, whatever it's starting from. Usually it's 0 or 1, but AN equals A. It can start from any constant, really. Given that series, suppose we set AN equals to some function, right? So there's a formula for the AN, obviously, and I'm thinking of it as a function. And consider this a real value function. Then, here's the scenario. If these situations are fulfilled, first of all, your f of x is never negative. It's always greater than or equal to 0. Second of all, your f of x is continuous on the interval. So it's always non-negative. It is always continuous for all these values. And next, f of x is decreasing. Now, of course, remember what it means to be decreasing. It means the derivative is less than 0. Okay. So here, I have a series, has some random formula to it. If I think of that formula as some function, and I notice these things are true about the formula, then, so if all of this is true, then the series that I'm considering, n goes from a to infinity of a to the n, and the improper integral from a to infinity of f of x dx will both converge or both diverge. In other words, they'll do the same thing. They will behave in exactly the same way. Now, the improper integral, I'll be able to compute in theory, and so whatever the integral does, the original series is going to do. Now, one of these, that's called the integral test. Now, one of these directions is kind of obvious that, yeah, that it would of course work out, because it's harder to get the integral to converge than it is to get the series to converge. Right? So now, if you look at what this guy actually looks like, it means you have some function that's moving down as you go off to infinity, and you are finding the area under the curve from a to infinity. Right? So now, that area actually exists. What would the kind of the series picture look like if I'm looking at n goes from a to infinity? That is a guy that actually only works on the integers, right? So he works at a, he works at a plus 1, he works at a plus 2, he works at a plus 3, etc. Right? The series will only be adding up things right here, but it cannot work in the class. Right? So the series is basically going to add the number here, then add the number here, then add the number here, then add the number here. But the integral is adding up those numbers, plus it's actually finding the area under the curve in between all these numbers. This guy is for sure going to be larger than or equal to that guy. So if this guy converges, then that guy has to converge as well. One, because it's non-negative, it's always positive, so it's adding up to something. It's never going to diverge to negative infinity. This guy is always going to be larger than 0. So the series is going to be stuck between 0 and this integral. And this integral, if it converges, it forces that guy to converge. Kind of like a comparison theorem. So it's actually harder to get this guy to converge. And so whenever that guy converges, that guy is going to converge as well. The other way, if this diverges, the fact to show that that diverges is a little bit harder to show, but this at least gives you some intuition for one of the directions here. It's harder to get the integral to work out than it is to get the series to work out. And so that's basically the idea behind the integral test. Now, this isn't strictly a requirement of the integral test, but of course for Calc 2, this is going to be a requirement. Calc 2 requirement. F of x should be easy to integrate. By easy to integrate, I mean looking at f of x, you should be able to tell, you know what, I know an integration technique that can deal with that guy. So you're looking at a series, and what you notice is, you know what, if instead of a series that was an integral, I actually wouldn't have any problem doing that. If you have that kind of thought, the integral test is probably going to be a good test to use, provided that you have these three properties being fulfilled. And you can actually determine what the series is doing by what the integral is doing. So let me give you an example here. You look at, say, e to the 1 over n divided by n squared. Let's say I threw that series already. Now, the limit of that does approach 0, so test for divergence not going to help you. It's definitely not telescoping, can do a partial fractions because of the exponential. It's also not geometric because of the n squared. You need the n to be in the power in order for it to be geometric. It has to be a constant to the nth power. So none of the tests that I mentioned before is going to help you out here. However, you can notice the following fact. If we set f of x to be equal to e to the 1 over x, right? So I'm not thinking of it as a series. Think of it, don't think of this as a sequence. Think of it as a function. So pretend that you can take on any value, not just integer values. You're going to notice certain things. One, you're going to notice that f of x is always going to be positive. In fact, that's going to be strictly greater than 0 on the interval, 1 to infinity. That's one thing you're going to notice. You are also going to notice that f of x is continuous on 1 to infinity. Right? Because the exponential is always going to be continuous as long as 1 over x is continuous, and 1 over x is continuous on 1 to infinity. And you're dividing by x squared. The only problem there would be dividing by 0, but you're never dividing by 0 because you're on the interval 1 to infinity. So that guy is continuous on that interval. Second of all, third of all, actually, first, second, third of all, if I were to take the derivative, what would I get? Well, it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So that is going to be, well, minus e to the 1 over x. That cancels that. It's going to be 1 plus 2x over x to the 4th. Now, x to the 4th, always positive. 1 plus 2x, always positive when your x is 1 or larger. E to the 1 over x, always positive. But then we have a negative sign out here, which means this is always negative. So f is decreasing. So here, I'm given a random series. The limit approaches 0, can't use test for divergence, not geometric, not telescoping. What could we do? Notice these three things are true if I think of this as a function instead of a sequence. And we have the Cal 2 requirement. This should strike you as something that is easily integrable. Now, I'm not sure if that would stand out to you, but it should, right? How would you integrate that? For it to integrate from 1 to infinity of e to the 1 over x squared.
Life works?
No.
No.
Remember you're training grasshoppers. What is the strategy? What is the first thing you try to look for? It's a basic rule. It's not a basic rule. Okay. Simplify till that a basic rule. No. Would a substitution work? Would a substitution work? If you were going to get a substitution to work, what would you substitute?
X squared?
Alright. No.
1 over x. What makes this complicated is the power of e. Right? Remember this guy? That guy should be like a warning to you guys. Messing with the power of e, if you change it from something that's just an x to something else, that's crazy. You can get into a lot of trouble, right? That guy is actually impossible to solve. The 1 over x makes that complicated. If I were to do that by substitution, I would substitute u equals 1 over x. Now, if my u equals 1 over x, what would my du be? Minus 1 over x squared. It's a substitution problem, right? So I can do that integral easily because it's just a substitution. You can see the derivative of the power is just a factor right there. So now we just have to do that improper integral. And based on what that improper integral does, is going to tell us about this guy. If this integral diverges, that guy diverges. If this integral converges, that guy converges. So now we've reduced the series problem to an improper integral problem. And so if you have 1 to the infinity of e to the 1 over x squared dx, you can do substitution. This will be minus e to the 1 over x from 1 to infinity. Yes, I know I'm supposed to do limit as n approaches infinity of 1 to, right, okay, we've been there. Plug in infinity here, you get e to the 0, you get minus 1, minus what becomes a plus. Plug in 1 for x, you get e. So the integral converges. And this means the series converges. And you would say by the integral test. Or by the int test. So that's another thing you can do, the integral test. One other option, one other tool in our tool belt. You're given a series, if you notice 3 scenarios that happen if you think of this sequence as just a regular real value function. If it's positive or non-negative, continuous and decreasing, and you realize that you know how to integrate that thing easily, which means you need to be very good at integration. You should be able to spot that you can integrate that easily. Then, what the improper integral does is going to tell you exactly what the original series does. That guy converges. Now I don't know what it converges to. I want you to be aware. This is what the integral converges to, not the series. The series converges to something smaller than that. Because like I said, the integral is adding up something bigger. It's adding up all the gaps that the series doesn't worry about. So that is the integral series, the integral test. Now, I'll give you more examples later, so we'll just do that one example and move on. Because eventually, like I said, we're going to combine various kinds of series and wanting to do them all at once, and you'll have to figure out what test to apply. So at some point, when I summarize all the techniques that we're learning, I'll give you some more examples. But again, when you should use series, these are things you should be taking notes of. So the integral test is very useful if you're looking at something that you know how to integrate very easily. Right. So let's do the integral test implies a lot of things. Let's talk about pSeries, the pSeries test. So this was mentioned earlier. Let's look at what these guys are talking about. Definition. A p-series is one of the form series from 1 to infinity of 1 over n to the p. Specifically that form. P is a constant. And it's allowed to be anything. It can be 0, it can be something else. That's a p-series. Now, if we notice that if we set an equals, well, an is going to be 1 over n to the p, think of this as some function, then your f of x is going to be 1 over x to the p. Now, that guy's going to be continuous as long as x is not 0, and your n is starting from 1, so it's not 0. This guy here is going to be positive. He is going to be continuous, and he's going to be decreasing. So you can actually apply the last test that we did, the integral test. This guy converges if and only if the integral of 1 over x to the p converges. So they're both going to, the if and only if means it goes in both directions. If one converges, the other one converges. If one diverges, the other one diverges. So the summation from 1 to infinity and the integral from 1 to infinity are both going to behave in exactly the same way. I can get that directly from the integral test. And it turns out, we actually know about this integral. We actually took a long time to prove exactly when that guy converges. When does that guy converge? When p is greater than 1. So now if p is strictly greater than 1, that guy converges. So that will tell you that the series is going to converge as long as your p is greater than 1. Theorem. So this converges if and only if p is larger than 1. So the integral test implies that 1 over n to the p converges if and only if p is larger than 1. And that is the p-series test. And it's basically the test that says, if you see a series 1 over n to the p, it converges if and only if p is larger than 1, meaning it will diverge in all other cases. If your p is equal to 1 or less than 1, it will diverge. One thing you can note, the harmonic series is a p-series. This was mentioned earlier. P equals 1 for the harmonic series, right? That guy gives you 1 over n to the first power, right? So we can know that that diverges by the integral test. One of many ways that we know that diverges. While the series of 1 over n squared, we mentioned earlier that that converges, and the p-series test actually coincides with that. And that's it. You see something that looks like that, you know it converges as long as your p is greater than 1. I'm going to give you some examples just as a formality, but this one is supposed to be really easy. In fact, there will never be a point where I'm going to ask you directly about a p-series. The p-series guys are going to be useful in comparing them to something else, because just looking at one of them, it's entirely trivial to know that they converge. It's not going to be hard. The worst that I can do, which since algebra class is not bad at all, is just try to write n to a power in some weird way. Harmonics is a very important series, so I'm going to put it as the first example. 1 over n squared, we spoke about that. So 1 over radical n. So that's a hard one, because it doesn't look like n to the p right away, but it is an n, 1 over n to the p. What's p here? A half, right? So that's 1 over n to the half. So these guys are all pSeries. Do these converge? Does this converge?
Nope.
No. Does this converge?
Yes. No. Yes.
Right, see, they're like super easy. But I'm never going to ask you directly about one of these. Usually, it's going to be something a lot more complicated that you can connect to one of these that you know about easier, and you're going to use this to talk about the other guys. So we're going to use these mostly in a comparison kind of way. There are theorems for series that are analogous to the comparison theorems for improper integrals because of the integral test. So that's important. But basically, you would say, if I ask you about these, you say, oh, this is a p-series, the p equals 1, therefore it diverges. And then you'll say, this is a p-series, the p equals 2, convergence. This is a p-series, p equals a half, convergence. Divergence. This is a p-series with p equals 11 over 10. That's greater than 1, so it converges. Right. So the solution here, they're all like one-liners. We'll write them out as a formality next time, but next time we will move on to the next test. We will stop there. I will figure out how we're going to continue the class, but at the very least, I'm going to continue to do these videos. I'll lecture to an empty classroom if necessary. Be all alone. Yeah, maybe if the math department forces me to do something interactive, I'm going to have to come up with something else. But at least the videos I'm going to keep doing.
Okay, Professor. So for the next 5 days, will there be like any online classes for any class, or just completely 5 days of like nothing?
Oh yeah, no, I'm going to keep going. Like, so,
Oh,
yeah.
How about quizzes?
So quizzes are suspended until we figure something out.
can you put that?
1 over, just 1 over n, the harmonic. So quizzes are suspended because to not give those in person, that's going to be kind of weird. We have to figure something out there.